Welcome to Organic Chemistry, Principles and Mechanisms by Joel Carty. Chapter 12, Electrophilic Addition to Nonpolar Pi Bonds 2. In Chapter 11 of Carty, the focus of discussion was the two-step addition reaction to carbon-carbon pi bonds. In the first step of this reaction, a proton electrophile is added to the pi bond and a carbocation intermediate is generated. In Chapter 12, the first step will be the addition of an electrophile other than a proton. These additions typically lead to a cyclic intermediate, where the positive charge is not necessarily located on a carbon atom. When a proton adds to a pi bond, the carbocation formed is relatively unstable due to the loss of an octet of electrons. If, instead of a proton, an electrophile with non-bonding electrons adds to the pi bond, it is possible to form a cationic intermediate where no atoms have lost their full octets. It would be expected that this leads to a more stable intermediate. These intermediates are typically cyclic in structure, as the electrons of the pi bond and the electrons from the electrophile form two sigma bonds simultaneously. One important consequence of the simultaneous formation of these two bonds is the conservation of the stereochemical relationships of the original pi bond. Groups which were cis to each other in the original pi bond will be cis in the cyclic species formed by addition of the electrophile. If the cyclic product is chiral, then a mixture of stereoisomers is produced, since the electrophile can add from either face of the pi bond. If the starting alkene was achiral, this will be a racemic mixture. Otherwise, a mixture of diastereomers will be formed. A carbene is one type of electrophile that adds to alkenes. A carbene contains a carbon atom that has two bonds and two electrons. The formal charge on a carbene is 0, but the carbon lacks a full octet, which makes it a strong electrophile. Carbenes are highly reactive species and are not readily isolated. Typically, a precursor molecule is added to an alkene and then reacted to form the carbene, which then quickly adds to the pi bond. In the example shown, diazomethane is the precursor to the carbene. On irradiation, diazomethane loses nitrogen to form the carbene, which then adds to the central pi bond to form a cyclopropane ring. Diazomethane itself is difficult to handle, as high concentrations can be explosive. Dichlorocyclopropanes can be generated by reacting chloroform, trichloromethane, with a base in the presence of an alkene. Chloroform will react with the base to generate dichlorocarbene in a two-step mechanism. The highly reactive carbene then can add across the double bond of the alkene. Bromine can react with cyclohexene to produce a racemic mixture of trans-1,2-dibromocyclohexanes. This reaction follows the general rule that achiral starting materials produce either achiral or racemic products. However, the reaction is stereospecific in that no cis-dibromocyclohexane is produced. The addition does not proceed through an intermediate carbocation. That could lead to a mixture of cis and trans products. Instead, a cyclic bromonium ion is formed as the intermediate, along with the bromide anion. One of the new carbon-bromine bonds in the intermediate will then be cleaved by SN2 attack by the bromide anion. Because all the atoms in the intermediate bromonium cation retain an octet, this species is actually more stable than a carbocation, even though there is a positive charge on the electronegative bromine atom. Chlorine undergoes the same type of addition to alkenes to generate 1,2 or vicinal dichlorides. This reaction proceeds through a similar intermediate chloronium ion, and the addition of the chloride anion occurs anti to the ring chlorine. Terminal alkynes will react with one equivalent of bromine to produce a mixture of E and Z 1,2-dibromo alkenes. The fact that a mixture of stereoisomers is formed indicates that the reaction does not proceed through a cyclic bromonium-like intermediate. The presence of the double bond in the ring would make this type of intermediate highly strained, so a carbocation may actually be preferred in this case. If an excess of bromine is used, a 1,1,2,2 tetrabromoalkane is formed. Halohydrins are compounds that contain a halogen and a hydroxyl group on adjacent carbon atoms. They can be formed when an alkene is halogenated in aqueous solution. In this example, the reaction of cyclohexene with bromine in water leads to the formation of racemic trans-2-bromocyclohexanol, a bromohydrin. The addition proceeds with the two new groups stereospecifically adding anti to each other, similarly to the halogenation reaction seen earlier. As may be expected based on the products, the mechanism of the addition is also similar to what is observed for halogenation. As seen before, the first step in the addition is the formation of an intermediate bromonium ion. Although bromide is the stronger anionic nucleophile, water is present in much higher concentration and will act as the primary nucleophile to displace the bromine atom from one carbon on the ring. When the alkene is unsymmetric, a mixture of two retioisomers can form. The isomer with the bromine atom on the least substituted carbon is the predominant isomer. The basis for this regioselectivity is similar to what was observed before in the ring opening of epoxides under acidic conditions. The electronegative bromine will withdraw electron density from its two carbon-bromine sigma bonds to alleviate the positive charge. This gives the two carbon atoms a partial positive charge. The carbon atom that can most easily accommodate the charge will have the highest positive charge. This atom will be most subject to nucleophilic attack by the solvent in this reaction. It is worthwhile to note that the halogenation of unsymmetrical alkenes probably proceeds in the same manner, but the nucleophile in that case is identical to the leaving group. Previously, we have seen that water can add across double bonds in the presence of a strong acid catalyst. An alternate method for the addition of water is oxymercuration followed by reduction, also called oxymercuration demercuration. In the example shown, 3-methyl-1-butene is reacted with mercuric acetate in aqueous tetrahydrofuran and then treated with sodium borohydride to produce 3-methyl-2-butanol. Hydration of this alkene with aqueous acid would generate 2-methyl-2-butanol as the primary product via an intermediate rearrangement. Oxymercuration reduction generates the expected Markovnikov product. However, the mechanism does not involve an intermediate carbocation that could be subject to internal rearrangement. Instead, a cyclic mercurinium ion is formed, analogous to the cyclic halonium ion seen before. This ion is more stable than a carbocation, and so does not undergo a rearrangement prior to nucleophilic attack by water at the most substituted carbon atom, opening the three-membered ring. Reduction of the product with sodium borohydride replaces the mercury with a hydrogen to give the final product. Cleavage of the cyclic mercurinium ion by water proceeds by anti-addition. The subsequent reduction step scrambles the stereochemistry, giving a mixture of syn and anti-addition products. Alkynes can also be hydrated by mercuric salts. The reaction does not require a subsequent reduction step, and the intermediate enol that is formed by hydration typically tautomerizes to a more stable ketone. In this mechanism, the cyclic mercurinium ion reacts with water to form a mercuric enol, which then tautomerizes to a mercuric ketone. Protonation of this intermediate ketone leads to the enol with displacement of the mercury ion. Because of this displacement step to the enol, the sodium borohydride reduction step is not necessary. Oxymercuration of terminal alkynes selectively generates methyl ketones. If an internal alkyne undergoes this reaction, typically mixtures of the two possible ketones are generated.